Welcome to our deep dive into the amazing world of network architecture. You know, it's incredible how much we rely on networks every single day, from checking emails to streaming our favorite shows. But have you ever stopped to think about what goes on behind the scenes? That's what we're unpacking today. We're going to explore how networks are designed, built, and even how they can be virtualized.
It really is fascinating how this intricate web of connections underpins our digital lives. And the cool thing is it's not just for IT pros. Understanding network architecture can give anyone a better grasp of how the digital world works.
Absolutely, and we have a fantastic guide for this journey, the CompTIA Network Plus Guide to Networks 10th edition. It's packed with insights. We'll start with the fundamental building blocks of any network: switches.
You can think of a network like a bustling city with data packets zipping around like cars. Switches act as those all-important intersections directing traffic to the right destinations.
Okay, that makes sense. So just like we have different types of intersections in a city, are there different kinds of switches?
Exactly. They're unmanaged switches, which are like simple roundabouts. They just keep the data flowing but without much control. Then we have managed switches, which are more like sophisticated traffic lights, allowing for fine-grained control and optimization of the network.
So if I wanted to set up a small home network, I'd probably just need an unmanaged switch, right?
That's a great example. For a simple home network, an unmanaged switch is usually sufficient. But for larger networks, especially in businesses, managed switches are crucial because they offer more control and security.
Speaking of security, our source emphasizes the importance of switch port security. It sounds pretty self-explanatory, but why is it so important?
Think of it this way. In our city analogy, it would be reckless to leave any building doors unlocked, right? Similarly, any unused ports on a network switch should be disabled to prevent unauthorized access.
So it's like locking the doors to rooms in your network that you're not using. Simple but effective. Are there other security measures besides disabling unused ports?
Absolutely. One important technique is MAE filtering. Every device on a network has a unique MBINC address, like a digital fingerprint. ME filtering is like having a guest list for your network. You can configure the switch to only allow devices with specific MC addresses to connect.
Wow, that adds another layer of security. It's like having a bouncer at the door of your network, making sure only authorized devices get in.
So we've covered the basics of switches and their importance in network security. But what happens when we need multiple paths for data to travel? Is that even a thing?
It definitely is, and it's a crucial concept called redundancy. Having multiple paths is like having alternate routes in our city analogy. It's fantastic for avoiding traffic jams and ensuring smooth flow even if one road is blocked.
That makes a lot of sense. But I can imagine having multiple paths could also create problems. Like, wouldn't the data packets get confused and end up going in circles?
You're absolutely right. Multiple paths can create loops where data packets get stuck in a continuous cycle, like cars going round and round a roundabout forever. That's where the spanning tree protocol, or STP, steps in. Okay, STP to the rescue. What exactly does it do?
Imagine STP as a super smart traffic management system for your network. It analyzes all the available paths and intelligently blocks certain paths to prevent loops, ensuring that data packets travel along the most efficient route.
So STP is like a navigation system that not only finds the fastest route, but also prevents traffic jams. Our source also mentions newer technologies like RSTP, TreeRLL, and SPB. What are those all about?
Think of those as the next generation of traffic management systems. They're designed to improve upon STP and make data flow even smoother and faster, especially in large, complex networks.
So we've got our traffic flowing smoothly with switches and STP, but networks are more than just a flat landscape, right? They need some structure.
You're spot on. Just like a city has different zones and districts, networks often use a tiered architecture. This involves having different layers, each with its own purpose.
Okay, break down those layers for me. What are they and what do they do?
Traditionally, we have three main layers. The access layer, where devices like computers and phones connect to the network. The distribution layer, which aggregates traffic from multiple access switches and connects to the core layer, which is the high-speed backbone of the network.
So the access layer is like the local streets, the distribution layer is like the main roads, and the core layer is like the highway system.
That's a perfect analogy. But just like cities evolve, network designs are constantly being refined. Our source mentions newer designs like the spine and leaf architecture, which simplifies things and makes networks faster and more scalable.
Spine and leaf, that sounds intriguing. What's the big idea behind that design?
Spine and leaf architecture is all about streamlining the flow of data. It creates a more direct and efficient path for data to travel, sort of like having a network superhighway with fewer on and off ramps.
I'm starting to see why network architecture is so fascinating. It's a constant evolution of finding better and faster ways to move data. But what happens when things go wrong? We all know how frustrating it is when networks go down.
That's where the concepts of high availability and fault tolerance come in. These are all about designing networks that can stay up and running even if some components fail.
Okay, so it's like having backup systems in place just in case something breaks down. What are some techniques for achieving high availability and fault tolerance?
One key technique is link aggregation, where we combine multiple network connections into a single, faster connection. It's like having multiple lanes on a highway, which not only increases capacity, but also provides redundancy. If one lane gets blocked, traffic can still flow on the other lanes.
That's a great way to keep things running smoothly.
Yeah.
Are there any other tricks up the sleeve of network architects?
Load balancers are another crucial component. They distribute traffic across multiple devices, ensuring that no single device gets overloaded. It's like having multiple cashiers at a busy store, preventing long lines and ensuring that customers are served quickly.
Makes perfect sense. So link aggregation ensures a robust connection, and load balancers distribute traffic to prevent overload. It's all about keeping things running smoothly, even in the face of unexpected issues. Now, let's dive into a topic that sounds like something out of a sci-fi movie. Virtualization.
Virtualization really is revolutionary. It's all about creating virtual versions of things like servers and networks, allowing us to run multiple virtual machines on a single physical machine.
Okay, my mind is officially blown. How does that even work? Is it like creating a whole network inside a computer?
You're getting the idea. The key to virtualization is software called a hypervisor. Think of it as a platform that sits between the physical hardware and the virtual machines, allowing them to share resources and access the network.
So it's like the hypervisor is the conductor of an orchestra, making sure all the virtual machines play together nicely.
That's a great way to put it. There are different types of hypervisors, but the concept is the same. Create a virtual environment where multiple operating systems can run simultaneously on a single physical machine.
This opens up a whole new world of possibilities. But how did these virtual machines connect to the network?
Each virtual machine has its own virtual network interface card, or VNIC. It's like a physical NIC, but for the virtual world, connecting the VM to the network. And what's fascinating is that we can configure these VNICs in different ways to control how the virtual machine interacts with the network.
So it's like choosing different types of connections for your virtual machine, depending on how you want it to interact with the outside world. Tell me more about these different configurations.
There are three main modes: bridged, NAT, and host only. Bridged mode makes the virtual machine act as if it's directly connected to the physical network, giving it its own IP address and allowing it to communicate with other devices as if it were a physical machine.
So it's like giving the virtual machine its own independent identity on the network. What about NAT mode? How does that work?
In NAT mode, the host machine acts as a middleman, sharing its IP address with the virtual machine and translating the traffic between the VM and the outside world. It's a bit like having a receptionist handling all the calls for a company, directing them to the right employee even though the caller only has the main company number.
So NAT mode is like giving the virtual machine a shared phone line, where the host acts as the operator. And what about host-only mode? Our source mentioned that too.
Host-only mode is like creating a private network just for the virtual machines. They can communicate with each other and with the host machine, but they can't access the outside world.
Got it. So bridged mode gives VMs direct access, NAT mode uses the host as a translator, and host only keeps everything isolated. That's fascinating. But I'm guessing there's more to virtualization than just connecting VMs to the network, right?
You're absolutely right. Virtualization offers a ton of benefits like efficient use of resources, cost savings, and easier backups. But it also has its complexities and potential drawbacks like performance issues and security concerns.
So virtualization is a powerful tool, but it's not a magic bullet. It's important to understand both the pros and cons before diving in. But there's one thing I'm really curious about. You mentioned that virtualization is about creating virtual versions of things, not just servers. Does that mean we can virtualize network functions too?
You're thinking about network function virtualization, or NFV. And yes, it's a game changer. It's all about taking traditional network devices like routers and firewalls and turning them into software that can run on virtual machines.
Whoa, so instead of having a bunch of physical boxes for routers, firewalls, and other network functions, we can virtualize them and run them all on a single server.
Exactly. That's the power of NFV. It allows us to be much more flexible and efficient in managing network resources. Imagine being able to spin up a new firewall or router in minutes just by deploying a virtual machine. It's a whole new level of agility and scalability.
That's incredible. So we've gone from physical switches to virtualized networks, and now we're talking about virtualizing network functions themselves. Is there an end to this virtual revolution?
It certainly doesn't seem like it. And it's leading to some truly amazing advancements like software-defined networking or SDN. But we'll have to save that mind-blowing topic for part 2 of our deep dive.
Okay, I can't wait to hear about SDM. But for now, I think we've covered a lot of ground. We've learned about the essential role of switches, the importance of network security and redundancy, the different layers of network architecture, and the fascinating world of virtualization. It's been an incredible journey so far.
It has indeed. And we're just getting started. Stay tuned for part 2, where we'll delve into the revolutionary world of SDN and explore how it's shaping the future of network management.
Welcome back to our deep dive into network architecture. Before we jump into the mind-blowing world of SDN, I'd love to dig a little deeper into virtualization. We touched on the different ways virtual machines can connect to the network: bridged, NAT, and host-only modes. But can you give me some real-world examples of how those are used?
Absolutely. Imagine you're setting up a testing environment for a new software application. You might create several virtual machines, each representing a different component of your system, and use bridged mode to connect them. This way, they can all communicate as if they were on a separate physical network, allowing you to test interactions and performance without affecting your production environment.
So it's like having a mini network within your computer specifically for testing. That's super convenient. But what about NAT mode? When would you use that?
NAT mode is a great option when you want to give your virtual machines access to the internet without assigning each one a public IP address. Think of it like a large office building with a single public phone number. Incoming calls are routed through a receptionist, who then directs them to the appropriate person or department. In this case, the host machine acts as the receptionist, sharing its IP address with the VMs and translating the traffic between them and the internet.
That's a brilliant analogy. It helps me understand how NAT mode conserves IP addresses and adds a layer of security by keeping the VM somewhat hidden behind the host's IP. And what about host-only mode? When is that useful?
Host-only mode is like creating a private network just for your virtual machines. It's a great option for development or testing scenarios where you want to isolate the VMs from the outside world. For example, if you're developing a new web application, you could create a host-only network with a web server VM and a database VM, allowing them to communicate securely without any external access.
So each mode serves a specific purpose. Bridged for direct network access, NAT for shared internet access with added security, and host-only for isolated testing and development. This is making me realize just how powerful virtualization can be. Now let's switch gears and talk about network redundancy. We discussed its importance in ensuring high availability and fault tolerance, but how does that play out in real-world scenarios?
Link aggregation is a great example of network redundancy in action. Imagine you have a critical server that needs to be constantly available, like one hosting your company's website. With link aggregation, you can connect that server to the network switch using multiple network cables. This not only increases the bandwidth, think of it like having multiple lanes on a highway, but also provides automatic failover. If one cable fails, the others instantly take over, ensuring continuous connectivity.
So it's like having backup internet connections at home. If one goes down, you automatically switch to the other. That's clever. What about load balancers? Our source mentioned those too. How do they contribute to redundancy?
Load balancers are essential for distributing traffic across multiple devices, ensuring no single point of failure. Imagine a popular e-commerce website during a big sale. Instead of having all the traffic hit a single server, a load balancer intelligently distributes the requests across multiple servers, preventing any one server from becoming overwhelmed.
It's like having multiple cashiers at a busy store, right? You can keep the lines moving and ensure that customers are served quickly. And if one cashier needs a break, the others can handle the load. That makes perfect sense. So link aggregation ensures a robust connection, and load balancers distribute traffic to prevent overload. Both play crucial roles in building resilient networks that can handle unexpected issues.
Exactly. And that brings us to the revolutionary world of cloud computing. The cloud has become so ubiquitous we use it for everything, from storing files to running complex applications. But what exactly is it?
I'll admit the cloud sometimes feels a bit nebulous to me. Like, is it just a bunch of servers somewhere?
It is a network of servers, but it's much more than that. The key to cloud computing is that it provides on-demand access to computing resources, servers, storage, networking, software as a service. Think of it like electricity. You don't need to own a power plant to use electricity. You just plug in and pay for what you use.
So instead of companies having to build and maintain their own data centers, they can just tap into the cloud and pay for what they need. That sounds incredibly cost-effective.
That's one of the big benefits of cloud computing. It eliminates the upfront costs and complexities of building and maintaining your own infrastructure. But the cloud is not just about cost savings. It also offers incredible flexibility and scalability. You can easily adjust your resource consumption as your needs change, scaling up or down as required.
That's amazing. It's like having a network that can grow or shrink on demand, just like a balloon. But the cloud isn't just one giant entity, right? Our source mentioned different cloud service models.
You're absolutely right. There are three main service models: infrastructure as a service, infrastructure as a service, ARS, platform as a service, PaaS, and software as a service, SaaS. Think of these as different levels of service at a restaurant.
Okay, I love analogies. Tell me more.
With IaaS, you're basically renting the kitchen space. You get the servers, storage, and networking, but you're responsible for everything else, like installing and managing the operating systems, applications, and data. It gives you a lot of control, but also requires more technical expertise.
So it's for those who like to cook their own meals, so to speak. What about PaaS?
PaaS is like having a preset menu. You get a platform with pre-configured operating systems, databases, and development tools, allowing you to focus on building and deploying your applications without worrying about the underlying infrastructure.
That sounds like a great option for developers who want to speed up their workflow and don't want to get bogged down with infrastructure management. And finally, what about SaaS?
SaaS is like ordering a fully prepared meal. You get a complete software application delivered over the internet, like email, office productivity suites, or customer relationship management CRM systems. You just subscribe to the service and start using it. No need to worry about installing, updating, or maintaining the software.
So IS provides the raw ingredients, PaaS gives you a preset menu, and SaaS serves you a complete meal. That's a fantastic way to understand the different cloud service models. But even with these different models, there are still choices to be made, right? Like, where is the cloud actually located?
That's where cloud deployment models come in. We have public clouds, which are owned and operated by third-party providers like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP. They're available to anyone and offer a wide range of services. Then there are private clouds, which are dedicated to a single organization and offer greater control and security. And we also have hybrid clouds, which combine elements of both public and private clouds, allowing organizations to choose the best option for each workload.
So it's like choosing between a public park, a private garden, or a combination of both. Each deployment model has its pros and cons depending on your needs and priorities. This has been incredibly insightful. Seeing these real-world examples of virtualization and cloud computing really helps me grasp these concepts. But I know we haven't even touched on SDN yet.
You're right. SDN is a whole other level of mind-blowing technology. But before we jump into that, let's take a quick recap of what we've covered so far. We've explored the different ways virtual machines connect to the network, dug into the importance of network redundancy with examples like link aggregation and load balancing, and demystified the cloud by understanding its key characteristics and different service models.
It's been an amazing journey, and I'm ready to venture further into the future of network architecture. Bring on SDN. Welcome back to the final part of our network architecture deep dive. We've explored the physical and virtual layers of networks, talked about cloud computing, and now it's time to step into the future with software-defined networking, SDN. I have to admit, the name alone sounds pretty futuristic.
It is futuristic. SDN represents a major shift in how we think about and manage networks. Imagine being able to control your entire network with software. That's SDN in a nutshell.
So instead of each router and switch doing its own thing, they all follow instructions from a central controller. Is that how it works?
That's exactly it. SDN centralizes the control of the network, taking the intelligence out of individual network devices and putting it into a software controller. Think of it like having a conductor leading an orchestra. Instead of each musician playing their own tune, they all follow the conductor's lead to create a harmonious symphony.
Okay, that's a helpful analogy. But what are the real benefits of having this central control?
Well, centralized control gives you incredible flexibility and agility. You can programmatically define network behavior, automate tasks, and respond to changing conditions much faster than with traditional networks.
Our source mentions SDN relies on this concept called disaggregation. It sounds pretty technical. Can you explain it in a way that even I can understand?
Of course, disaggregation is all about separating the control plane from the data plane. The control plane, which is managed by the SDN controller, is where all the decisions are made about how traffic should flow through the network. The data plane, which consists of the physical switches and routers, simply carries out those instructions.
So the SDN controller is the brains of the operation, making all the decisions, and the switches and routers are the brawn executing those decisions.
Right. You got it. This separation makes the network much more flexible and easier to manage. You can make changes to the network behavior without having to touch individual devices.
Wow, that's powerful. It sounds like SDN could simplify network management quite a bit, but can you give me some real-world examples of how it's being used?
Sure. SDN is making waves in many areas, from data centers and cloud environments to large enterprise networks. One example is in data centers where SDN can be used to create virtual networks on demand. Let's say a company wants to launch a new application. With SDN, they can spin up a dedicated virtual network for that application with just a few clicks without having to physically reconfigure the network.
So it's like having a network that can adapt and change instantly to meet the needs of the business. That's amazing. Are there other examples?
Absolutely. SDN is also transforming network security. Instead of configuring security policies on individual devices, you can define them centrally in the SDN controller and apply them consistently across the entire network. You can also use SDN to automatically detect and isolate security threats, preventing them from spreading.
So SDN is not only about flexibility and agility, but also about enhancing security. It sounds like a game changer.
It is, and is being driven by the increasing adoption of automation and orchestration in network management, which are crucial concepts mentioned in our source.
I was hoping we'd talk about those. We've touched on automation a bit, but can you explain what orchestration is and how it's related to SDN?
Well, think of automation as automating individual tasks. For example, you can automate the process of configuring a new switch or backing up network data. Orchestration takes automation to the next level by coordinating multiple automated tasks into a workflow. It's like having a conductor who not only directs the musicians but also choreographs their movements to create a visually stunning performance.
Okay, so orchestration is like the grand finale of network automation. It's about putting all the pieces together to create a seamless and automated system.
Exactly. SDN provides the platform for programmability and control, while automation and orchestration make it possible to fully leverage those capabilities. They allow us to build self-managing networks that can adapt, heal, and optimize themselves with minimal human intervention.
That sounds like the ultimate goal, a network that can practically run itself. It's incredible to see how far network technology has come. But with all these advancements, what are some key takeaways for our listeners? What should they keep in mind as they continue exploring this field?
One thing to remember is that the world of networking is in constant motion. New technologies are emerging all the time, so it's essential to stay curious, keep learning, and be adaptable to change.
That's good advice for any field, really. What else?
Network architecture is no longer just about physical devices. Software is playing an increasingly important role. A strong understanding of both hardware and software concepts is crucial in this field.
It sounds like the line between hardware and software is blurring, and software is becoming the driving force.
And finally, never underestimate the power of automation. It's transforming network management, making networks more efficient, agile, and secure.
So embrace automation, stay curious, and never stop learning. That's a great recipe for success in the world of network architecture.
I completely agree. It's an exciting field full of possibilities.
This deep dive has been an incredible journey. We've learned about the essential building blocks of networks, explored the revolutionary concept of virtualization, demystified the cloud, and stepped into the future with SDN. It's been a whirlwind tour, but I feel like I've gained a whole new appreciation for the complex world of network architecture.
I'm glad to hear that. It's a fascinating subject, and I hope this deep dive has sparked a desire to learn even more.
It definitely has. And for our listeners, I encourage you to continue exploring this ever-evolving world. There's always something new to discover, and the possibilities are truly limitless. Thanks for joining us on this deep dive into network architecture. Until next time, keep exploring, keep learning, and stay connected.